The law of conservation, of energy. The echoes rumble through the universe. What is the law of conservation of energy, Annika? Well, it starts out by saying that energy is neither created nor destroyed. If you want a poetic way to say it, when the Big Bang occurred, when all of the universe sprang into being, that amount of energy has never changed. We have never added energy to the universe. We've never removed energy from the universe. We have moved it, we can transfer it, we can transform it, we can change it from one type to another, but the amount of energy in the universe from day one, John, from moment zero, has remained constant. Energy is neither created nor destroyed. It can only be transformed from one type to another. Primarily, we're going to be looking at transforming energy from potential into kinetic or kinetic into potential, and some heat along the way. What this means is if we're looking at a closed system that has no outside sources of energy, we're not adding gasoline to the fire, Erica. We're not adding a battery to the device. We're not plugging in a motor. The total amount of energy at the start and the total amount of energy at the end must be the same. Sliding a block down a hill is a great example of conservation of energy. In fact, Ram, you can even do this in your head. If you read along with me, it says this. Both the KE, Ram, what's KE an abbreviation for? And the PE, what's PE an abbreviation for? Of a block sliding down the ramp are shown below. At the bottom, right here, Ram, what's the total amount of energy that I have? Do the math in your head. Say that again. How much energy do I have?
75 joules.
Conservation of energy, G says I'll have 75 joules anywhere else here. So if I have no kinetic energy, now the reason I have no kinetic energy is I'm starting at rest. How much potential energy must I have? Do it in your head. How much energy must I have grand total the whole time? So how much potential energy must I have if I have no kinetic energy? Yes. Have you ever ridden your bike down a hill? What happens as your height decreases? What happens to your speed? I'm going to ask you the same question. I'm just going to phrase it slightly differently. What happens to your kinetic energy? So here we've slid downhill. We've lost some potential energy. How much kinetic energy must we have? Do the math in your head. What? Yes. You're speeding up as you go down the hill. Now, all of you figure this out when you're about 5 years old, that if you ride a bike down a hill, you're going to speed up. This is the why of why that's the case. It's because the energy that you had from height has to go somewhere, and it's going to go into kinetic, into the energy of motion. Here, I have 50 joules of kinetic energy. I've sped up even more. How much potential energy must I have here? Yeah. Now, in real life, if I use real examples, the math, the numbers won't be so nice that you can do them in your head, but that's the idea behind what we're looking at over the next couple of days. The amount of energy you start with has to be the amount of energy you end with, and if I know how much of one type, I can figure out how much of the other type. In words, the law of conservation of energy, or C of E, says the amount of energy in a closed system never changes. As an equation, stored energy initial plus motion energy initial equals stored energy final plus motion energy final, except I tend to abbreviate. How do I abbreviate stored energy as 2 letters? Okay, so I can write this as PE initial plus, and how do I abbreviate motion energy? KE initial equals PE final plus KE final. I don't know what it is as a lefty. I have real trouble with capital letters. They're always messy, sorry. And the E is my bane of my existence. Those are terrible. E, final. I almost always start out, if I'm doing conservation of energy, Mason, by writing that out, but I can take it one step further. Mason, from your green formula sheet, what was the equation for gravitational potential energy? It's going to be in the work equals force times distance section there. By the way, I'm really encouraging you to start looking at your green sheet. I've seen a lot of people finding equations in their notes, but now you don't know where to look. You want to train your eyes where to look, and I'm stalling long enough. Mason hopefully has found it. Have you? It is MGH. So PE initial would be MGH initial. And Mason, what's the equation for kinetic energy? Probably right next to the MGH. Would make sense. or as we like to say, just a half mv squared. So a half mvi squared if it's initial, yes? And then it would be mgh final plus a half mvi squared. Oh, vf squared final. Vf squared. Okay. Sometimes these are 0. If you're at rest, your kinetic energy will be 0. Something will cancel. That's always nice. Or if you're on the ground, your potential energy will be 0. Yay. If we want to be even more accurate, Matteo, this is the law of conservation of energy in our magic physics world to keep the math nice. But in real life, you always lose a tiny bit of energy to heat. It's why we can't just start a machine going and walk away and have it keep going. It will gradually slow down and slow down and slow down because we're losing energy to heat. So if I want to be a bit more accurate, I could say this. Potential initial plus kinetic initial equals potential final plus kinetic final. If the numbers don't match, so for example, Ram, if on the block question you had 73 joules of energy, you would know that 2 joules of energy had gone into heat caused by friction. Really, this is heat and other dissipative energies. When you're riding your bike, you lose a lot of energy to air resistance because when you're bumping into the air molecules, you're giving them kinetic energy. That's why you may have noticed if someone bikes past you really quick, you feel the breeze. They've given those air molecules kinetic energy. That energy had to come from somewhere. It came from their pedaling. A great example of conservation of energy is a skate park. Here is my energy skate park, okay? And the reason this works is because energy, first of all, work is a scalar, and because energy is a scalar, it really handles curvy paths very, very well. Now, I have friction turned off right now, so what I'm going to do is I'm going to give this person potential energy. And then I'm going to let them go, and you can see the energy transform that's occurring. All of the potential is turning into kinetic, back into potential, back into kinetic, back into gravitational potential, back into kinetic, back into gravitational potential, back into kinetic. Levy, what do you notice about the total energy? Is it changing at all? That's the law of conservation of energy. The amount of energy you start with has to equal the amount of energy you finish with. At the top, Levy, for a split second, how fast am I going? As a number exactly. 0. So how much kinetic energy do I have at the top for a split second, Ange? So it's all potential energy, and that will happen at my maximum height. What about at the bottom? How much potential energy would I have at the bottom? What's my height at the bottom? 0. So what's my MGH at the bottom? So what's all of my potential energy turned into? Kinetic, and that's why you're going your fastest at the bottom. And again, you know this from being on rides. A swing set is another good example of conservation of energy. You're going your fastest at the bottom. But John, this is the why if that's the case. This is how come. Now, this is nonsense. In real life, you're losing some energy. So, Ange, I'm going to turn friction on now and watch what happens. You'll notice, Ange, the total energy isn't changing, is it? But you're noticing you're near the front. Can you read that word right there from where you are? Okay, you're near the front. Brendan, can you read that word? Thermal. Heat. More and more of the energy is being lost permanently to heat. And so we're not going as high. Because we're not going as high, we're not going as fast. Eventually, if I don't add energy to the system, I'm going to come to a stop. So for those of you who skateboard, this is why you have to kick with your feet or shift your weight. You have to add energy to the system or you'll come to a stop. But in our magic physics world, we're ignoring friction and air resistance. In theory, you should be able to keep going back and forth forever and ever and ever. But in the real world, this is the problem. We always end up losing most of our useful energy to useless heat that we can't get back. We have a fancy word for that. We call it entropy, and it's a law of the universe. Okay. So the skate park, a great example of conservation of energy. You're all waiting for this person to come to a stop, so I'll let it keep going back and forth. I got another great example of conservation of energy. I'm going to leave the recording on. Sorry for those of you on YouTube if you can't see this. This here on my whiteboard is my marble transfer device, my energy transfer device. You may have thought it was just a little marble track. No. What I do is I give this marble potential energy. Now, if I give it potential energy and just drop it, it will turn into kinetic, and almost all of the potential will turn into kinetic because this is aerodynamic, very little air resistance. However, I can also spread this out. If I give it potential energy and let it go, can you hear it? We're losing some energy to sound. That's moving, that took some kinetic energy. That's moving, that bled off some kinetic energy. That's moving, that bled off some kinetic energy. It still reached its baseline potential energy of 0, but with nowhere near as much kinetic energy, nowhere near as fast as if I just dropped it. Mr. Dueck, can we play with that later? If you finish the homework later on in class, if you ask me nicely, you can play with my energy transfer device that you may have just thought was a marble track. Please. Other great examples, bouncing a basketball. Those of you that have played basketball, at the bottom, it's all kinetic energy. That's why it's traveling the fastest, right when it hits the bottom. At the top, if it comes to rest, it's all potential energy. A pile driver is another really good example of an energy transfer. For a pile driver, you lift it up, giving it potential energy, and then it turns into kinetic energy upon impact. Let's do one with numbers. Now, example 1, there's a bit of a typo. I finally fixed it. Where it says a projectile, in between the words and projectile, can you put a little 12 kilogram? Let's give it a mass. A 12 kilogram projectile is launched straight up into the air. If its initial velocity was 84.3 meters per second, how high does it go? Use energy and ignore friction. Now, I have to be honest, Andrew, if I gave this to you, or if you gave this to me, I wouldn't use energy for part A. I would for part B, but I wouldn't use energy for part A. I would solve it like this. Don't write this down. I would say, well, they want me to find a height. That's a distance from before Christmas. I would say VI equals 84.3. Don't write this down. I would say at the top for a split second, what's V final? 0, and I know that A is negative 9.8, and I would use VF squared equals VI squared plus 2AD, and so I would end up going D equals VF squared minus VI squared all over 2A, and I would use that because it's quick, I'm really good at it, and it gets me there. But I also want to show you, Jess, you don't need to write that down, Jess, I want to show you that it works for energy, for conservation of energy. So since it said use conservation of energy, let's write this down. K E initial plus P E initial equals K E final plus P E final. Kinetic energy is the energy of motion. Is this ever 0? Is there ever a moment when this object is at rest? Oh yeah, you answered that just a short while ago. You said it's at rest at the very where? Top. So I can say that the final kinetic energy is 0 and I can cross it out. Yay. Initial is not 0. Initial is a half m times whatever 84.3 squared is. Half mv squared. Potential energy due to height is when I'm on the ground. Am I ever on the ground? Initial or final? Yeah. We all know PEI isn't a real province, right? They're a mayor, not a premier. Let's be honest. Right? And so we get kinetic energy initial equals potential energy final. What are the equations? What's the equation for kinetic energy? A half. It's on your sheet. Sorry? So kinetic energy initial is going to be a half m v initial squared. And potential energy, mgh, potential energy final is going to be mgh final. Nat, how many terms are there in this equation? Is there an m in the first term? Is there an m in the second term? Is there an m in everything? Then the m's cancel. You can divide by m, divide by m. You can do that. Now, if there isn't an m in everything, you can't do that. But if there's an m in everything, you would go divide by m, divide by m, divide by m, divide by m. It will cancel out. What am I trying to find, Nat? How would I get the h by itself? Yep. Now, there's two ways to write this. First of all, if you don't mind, I'm going to go h final equals. You can either make that 1/2 a 0.5. You can write it as 0.5 vi squared over g. I'm fine with that. Maggie, you know that I prefer to treat that 1/2 as a 1/2. I don't see a 0.5. I see a 1 on the top and a 2 on the bottom. I would write it as vi squared over 2g. Those two equations, Jess, are the same. I don't care which one you pick. To me, this one looks cleaner, but I don't care. Vi is 84.3. Don't forget the squared. All over 2 times 9.8. You may notice that I'm actually doing almost the same numbers as when I did the kinematics, where I told you don't write this down. When I used VF squared equals VI squared plus 2AD, it did end up with the VI being squared and the 2 and the 9.8 on the bottom. So we end up doing kind of the same thing. What do you get? This should go pretty high, because 84.3 meters per second, that's faster than a human being is going to throw. This should make it at least a couple of hundred meters up. Probably 300 or maybe even 400 if I'm doing the math right in my head. Brendan, what'd you get? 363. Anybody else? If I go to 3 sig figs, 363. Now, that's the theory. That's the theory. Supposing we did this and it only went 72 meters high instead of 363. What that means is this projectile is not very aerodynamic. There's massive air resistance. But it also means we've lost some energy. No, we haven't. It got transformed to something else. What did it get transformed into? We heated up the air. We made the air hotter. So B says, suppose the projectile only reaches 72 meters. How much energy was lost to air friction on the way up? Or how much work did air friction do slowing the object down? Or if you draw a little point and arrow to air friction, how much heat was generated? And when you move through air really quickly, heat is generated. It's a major issue for fighter jets, or they're talking about building jetliners that don't just go supersonic, they want to go hypersonic. But when you start doing that, the hull temperatures start reaching 3,000 and 4,000 degrees Celsius, and so aluminum is no longer what you can make your airplanes out of because it melts. I have to use conservation of energy for this. Now, the hint for that is energy, and they mentioned air friction or heat. So I'm going to take conservation of energy, KE initial plus PE initial equals KE final plus PE final. By the way, I've noticed on your formula sheet, Matteo, and this is on your formula sheet, I think I put the PE initial first. For some reason, when I write it from memory, I do kinetic first. Here's what the formula really is, Ethan. Initial plus initial equals final plus final. What you start with is what you end with. Except this time we're losing some energy to heat. I'll do it in red so it stands out. Heat. Whatever's left over went into heat. Tie, we have the same conditions as before. At the top, we come to a stop, so KE final is 0. And we started out on the ground, so Prince Edward Island isn't a province. I hope no one here is from PEI, or maybe my YouTube listeners are from PEI. Sorry, it's a dumb way to help kids remember. Levy, what am I trying to get by itself here? Nope. Psst, look up. Yeah. How much work air friction did, which we're going to call heat. So how am I going to get the heat by itself? Well, I have a plus PE final. How do I move the plus PE final over? Yep. What's going to drop down? Kinetic energy is going to drop down like a domino. So I'm going to have this. The KE initial drops down. You said, and I agree with you, Levy, minus PE final. And then do you mind? I'm going to put the heat over by itself on the left because that's where it's used to see. Kinetic energy is a half. Oh, sorry. Before I do that, let's rewrite this one more time on a new line. Heat equals a half mv initial squared minus mgh final. Natalie, how many terms are there this time? Is there an m in the last term? Is there an m in the middle term? Is there an m in heat? So is there an m in everything? So can I cancel an m out this time? Nope. It's going to be plug and chug. Heat is going to be 0.5 times 12 times 84.3. Was that how fast we started? Squared? Yeah, there it is. Minus 12 times 9.8 times the height we actually reached, which is only 72. How much extra energy did we lose to heat? Because that energy had to go somewhere. Really, the law of conservation of energy says energy's got to come from somewhere and it's got to go somewhere. You can't just magically conjure it out of existence or into existence. 0.5 times 12 times 84.3 squared minus 12 times 9.8 times 72. You get 34,171.74 joules. Yeah. I'm going to go 31,200, but I'm going to store this on my calculator. 34,200 joules. Now, here's one area where conservation of energy is nice. What does part C want me to find? This is air resistance. All year long so far, I've said to you, well, we can't really deal with air resistance because we need calculus. Actually, here is one time where we can calculate the force of air resistance. The average force. I still can't calculate it split second by split second by split second. I need calculus for that. How the heck am I going to do that? What did I find in part B, Amni? And in brackets, what else? What was another name for heat? The work done by? How do I calculate work? Work is what times what? So I'm going to argue that the work done by friction is the force of friction times distance. Is that okay? What am I trying to find, Amni? How would I get the force by itself? Oh, so you're saying, and now I can calculate an air resistance force, an average air resistance force, but still I can calculate it now. This would be measurable and calculatable. Friction equals the work done by friction, the heat, divided by the distance. I'm going to write 34,200, but I'm using my answer button, I guarantee it, divided by, which distance? More specific. 72, because that's the distance that air resistance was acting over, and they are in the same direction. So 72 divided by 72, and I get an average force of friction of 475 newtons. Is that okay? Mr. Dueck, why do you say average? Because I know how air resistance works. At the beginning, when it's going its fastest, air resistance would be its biggest, but it slows as as the object slows, air resistance gets smaller and smaller and smaller. You can turn the page and put your pencils down. It says Mr. Dueck has a very cool demonstration of conservation of energy. Let's start. Sorry for those of you in YouTube land that couldn't see that demonstration. We've learned a lot of physics this year. We started out way back when with kinematics, D and V and T. And the approach that I gave you there was the DFIC approach, list your data, final equation, just to give you a toehold. You'll notice I'm not being as fussy with that anymore because most of you are good enough that you're just seeing where to go right away. But then when we looked at forces, what was our strategy for forces? If I saw a mu or a normal force, it was a job for a free body diagram. That's another tool that I've given you. We looked at momentum, two objects colliding usually, or impulse. When do I use conservation of energy? Well, if I notice that there is a change in height, and at the same time there is a change in speed, and especially if there is a yucky curvy path, that's a job for conservation of energy. That yucky curvy path, because energy is a scalar, it means I can ignore what's going on in between. It means all I care about is where did I start and where did I end. That's all I care about. If I go to my skateboarder, for example, I can change the path to this if I want to. And if I turn friction off, still the same idea. Now, you'll notice on the way up, I lost a bit of kinetic and gained back a bit of potential, and then sped up down here all the way to the top. If I turn friction on, if I turn lots of friction on, if we have a really, really bad skateboard, might not even make it back up. Oh, I'll make it up there, but I'm probably going to get stuck in this little lip right here, I'll bet you. Oh, yeah. Got stuck right here. So this time, not all of the energy gets transferred to heat. There's going to be some potential energy left over because I never made it back down to the ground. Great examples or great areas to use conservation of energy. Ski hills, water slides, swing sets, and roller coasters. I guarantee there's going to be at least one, probably two, more likely three roller coasters on your test. There's going to be at least one roller coaster question on your test. So let's look at ski hills. First application. In location Z, a skier is traveling at 18 meters per second. How high up the next slope can the skier reach if we ignore friction? And you know what? Snow has very little friction. We're probably going to be reasonably accurate ignoring friction. Okay. Andrew, is there a change in height in this question? Hey, yes. Yeah. And will there be a change in speed in this question? And is there a yucky curvy path? This is a job for conservation of energy. So I'm going to write down KE initial plus PE initial equals KE final plus PE final. Make sure you know where that is on your formula sheet. I did give you the law of conservation of energy. I don't think I gave you the one plus heat. That's one I'll expect you to add if the question says figure out the heat. Andrew, are any of these zero? Is this person ever on the ground? Oh, you know what? Hang on, look up. Everybody, let's agree that this is initial and that's final. I think that makes sense. Yes? Andrew, is there ever a time we're on the ground? Where? Is there ever a time we come to a stop? Where? What's the equation for kinetic energy? A half m v initial squared. What's the equation for potential energy? M g h, and since it's final, it'll be h final. Andrew, how many terms are there in this question? Is there an m in the first term? Yeah. Is there an m in the second term? Andrew, do you ski or snowboard? Yeah. Have you been before? Yeah. Have you ever seen a grown-up holding the hand of a little 5-year-old or 4-year-old and skiing side by side? Yep, grown-up skiing with little kids. The fact that the mass cancels, that's why the grown-up can do that. If that didn't happen, the grown-up would have to be constantly snow plowing so that the little kid didn't get dragged along behind them so they didn't go scooting ahead of the little kid. But the fact that the mass cancels, the grown-up doesn't have to be constantly adjusting their speed. They can hold on to the hand of somebody with a smaller mass, no problem. Now, in real life, there is a tiny bit of friction, and so I have to be honest, in real life, the mass doesn't quite cancel, but it's small enough to be negligible that the grown-up doesn't notice the speed adjustments that they're making. It's not like they're having to go full snowplow or anything like that. Just a little nerd trivia. Andrew, what are you trying to find? Yeah. How high up? Which is h. How would I get the h by itself? Divide what? Let's use our nouns. Divide what? Divide g, yes. Yes, I want the h to stay, right? When you say divide it and I say get the h by itself, or you want me to divide the h? No, I want it to stay where it is. Divide the g over. So if I hear you correctly, first of all, do you mind, Andrew? I'm going to go h final equals. You're telling me the vi squared stays where it is. Divide by g. You can either put a 0.5 on top. I'm just going to tuck a 2 down there because to me that looks prettier. I've scrolled down, Andrew. How fast are we going at initial at point z? Thank you. All over 2 times 9.8. You're going to get an answer slightly less than 18, something in the 17 or 16 range, I think. Because this is almost 18 squared divided by 18, but it's 18 squared divided by a little bigger than 18. So you get an answer a little less than 18. Yes or no? What'd you get? 17 even? Can you give it to me the 3 sig figs? 16.5, yeah. Now, in real life, because in real life there would be some friction, probably 15.8, 15.5, something a little less. But you're not going any higher unless you add energy to the system by pushing with your poles. Now you've changed the question. Now it's no longer a closed system. You've decided to do extra work, force times distance. This is the law of conservation of energy. I like example 3. I like example 3. I like example 3. Example 3 is a nice question. This is the physics of my Nerf dart gun, but a bow and arrow. Suppose it takes an average force of 245 newtons to pull the bow back a distance of 68 centimeters. You know, the first thing I would do is say, nice try, Mr. Dueck. Cross out the 68 centimeters. How many meters? Sorry? 0.68 meters? Okay. Ty, what's A want me to find? Okay, how do I calculate work? Yep. Oh, the force and the distance have to be in the same direction. I'm looking at the picture. Check mark. So work equals force times distance. It's going to be 245 times 0.68. You get 166.6? I'm going to write down the whole thing because I think I'm going to be using that shortly. That's how much work I did in pulling the string away from the bow. B. Ethan B asks, how much potential energy is stored in the bow? How much potential energy is stored in the bow? Too slow. And I'm not meaning to make fun of you, but I'm saying the answer staring you in the face. How much potential energy is stored in the bow? Can you please read the number out loud? 166.6. Now, this is not gravitational potential energy. This is not MGH. This is stored energy. It's exactly 166 joules of energy stored in the bow. The potential energy here, not because of MGH, but because of work equals force times distance. I did work on the bow, storing energy in the bow, is 166.6 joules. If I know how much energy I've stored in the bow, I can tell you how fast the arrow is going to leave. I need the mass of the arrow. So it says if the arrow has a mass of 42 grams, nice try, Mr. Dueck. Cross out the 42 grams. Kilograms, how many? That's 420 grams. Kilo's 1,000, so you got to divide by 1,000. So there's always an extra 0. 0.042. How fast should it leave the bow? Jess, what's this asking me to find? Speed. And I'm glad you said speed and not velocity. We're going to be in a scalar land. What did I find in part B? In part B. That's how I know this is a job for conservation of energy. That thing that I said to you, is there a change in height? Is there a change in speed? Is there a curvy path? It doesn't always work, no pun intended. But this is going to be conservation of energy because I've just stored a bunch of energy and I'm turning it into kinetic. I'm going to say this. Potential initial plus kinetic initial equals potential final plus kinetic final. Are any of these 0? What? Yep, starting at rest. One more thing is 0. Once the arrow leaves the bow, does the bow have any more stored energy? The arrow has absorbed all of it as kinetic, so the final potential is 0. Now, a lot of kids say, Mr. Dueck, this is MGH. Not this time. It's not that we lifted the arrow up. It's that we did 166.6 joules of work. So it's going to be 166.6 joules. That equals a half mv final squared. Ethan, how many terms are there here? Is there an m in everything? Nope. Does the m cancel this time? Nope. How would I get the v by itself? Sure? Sure. And that equals, how do I get rid of a squared? Okay. So if I want to actually crunch this with the numbers, it's going to be the square root of 2 times 166.6. I'll use my answer button, divided by 0.042. What do you get? I tried to make these numbers reasonable. I hope this works. I hope this works okay. I have some water boiling over there if you're wondering. And that's for another demonstration that I'll show you next class, but I have to reset it each time. So it's being reset right now. What'd you get? What'd you get, Brendan? You get something in the 80s, I believe, yes? Sorry? 89 point what? And it's meters per second, it's a speed. 89.1? That seems about right. I've seen archers shoot. I can follow the arrow with my eyes, but I can't throw it that fast. A football field every second, which is roughly what 89.1 meters is, that seems ballpark figure about right. I don't think they beat the speed of sound. In fact, I know they don't. So, sure. 89.1? Is that what you said? Meters per second. My Nerf dart gun works exactly the same way. I store potential energy by going force times distance. In fact, I've measured the force and the distance to figure out how much energy I've stored in there. Not much, but some. When I pull the trigger, this potential energy turns into what type of energy? Kinetic. Kinetic. Okay? Not very much, and this is terribly inefficient. A couple of years ago, just for giggles, I ran the numbers to see how fast this Nerf dart gun should leave, and then I used a radar gun to measure how fast it actually leaves. I think this is like 6% efficient. You lose a lot of energy to heat and friction and sound and other dissipative forces. Although I think Adam Savage on his YouTube channel took one of these apart and really souped it up. If you're someone who likes to build these things, he really made it more efficient, and it came out pretty darn fast. We're going to pause here. Your homework is the take-home quiz. Your homework is also any other missing assignments. We'll finish this off next class.